this is it's a 50-cent piece. It's a half dollar, but more importantly, it's a circle. And so circles are important because we can use a circle to calculate the value of pi. If you measure the distance around the circle, that's circumference, and you measure the distance across the circle, the diameter, pi is a relationship between those two. Okay, so I want to do that, but I want to use you could grab a whole bunch of circles all over the place, but I want to use it do this with fake circles. Okay, so let me turn this off. So imagine that I have a circle. And I was able to create a circle, and I'm going to create this numerically. So the question is, how do I create a circle? Let's take the following. Suppose I have a pivot point right here and an object. And then there is some force pulling, a central force, F. And that force depends on this radius R. Now I give this some initial momentum P. Then what's going to happen is the force is going to pull it this way, and that means it's going to change direction, and it'll end up going right there. And then it'll eventually make some type of circular, maybe not even completely circular, orbit around there. If I can get this thing moving in a circle, then I can actually use that to determine how far around the circle it is and how far this is. I can make a model that moves in a circle. Okay, so there's a lot of parts here. Let's get to it. The first thing is, what's this force going to be? I'm going to say this. I'm going to say F equals negative KR. So R is the vector from the center location to my point, and K is just some constant. I can just pick a value. It's like a spring, but this is not a... Yeah, this would be like a spring. This is like a spring of zero distance. Okay, now I would have to use some initial velocity and momentum, P equals mv. But if I want to calculate exactly the velocity to make it move in a circle, I feel like that would be partially cheating. So if I give it some arbitrary initial velocity, it's not going to move in a circle. So what I want to do is to add an extra force. I want to add a force. Let's say I'm at this position. There's my center, and there's my velocity. So it's not moving in a circle, or otherwise these two would be perpendicular. So that's R, and that's the velocity or the momentum. I can find the component of the velocity in the radial direction. I'll call that R dot. Then I can have a drag force that is in the opposite direction as the radial velocity. So what that's going to do is, if it's moving away from the circle, that force is going to be pushing this way. If it's moving that way, it's going to be pushing towards. And eventually, this will go and kind of settle into a circle. Does that make sense? Think of it this way. If I had just a normal drag force that was perpendicular to the momentum, there would be a velocity component in the direction of R, but also in the direction of that it's moving. So it'd slow down, and it wouldn't go in a circle. But this way, it would. Now, how do I model the motion? Well, here we use the momentum principle. This is the basics of a numerical calculation. And I know I'm going fast just because I'm excited about pi. So if I say F net, which is going to be the sum of the spring force and the drag force, is equal to the change in momentum over the change in time. So this is the definition of the momentum principle. If I choose a very short time interval, then I can assume that F net is constant. So this is going to be P2 minus P1 over delta t. So this is the momentum at the end of the time interval, that's the momentum at the beginning of the time interval, and that's the length of the time interval. If I solve this for P2, I get this. P2 equals P1 plus F net delta t. So I can find, if I know the force, which I can find based on the momentum for the drag force and the position, and that's that other force, I can find that. And I know my momentum. I can find the new momentum at the end of the time interval. Now I can do the same thing for position. I can say V average is momentum over mass, and that's equal to the change in position over the change in time. So if I solve this for the final position, I get R2 equals R1 plus P, I'm going to say 2 over M delta t. So here's another trick, right? If I assume that the final momentum is the same as the average, which is not true, but with a short time interval, it's kind of true, then I can use this to find the new position, and then finally I can find the new time. And then I can just do the whole thing over again, but now recalculate the force based on the position and the momentum. Use that to update the momentum, use that to update the position, and then update time. And just keep going over and over again. And that's the idea of a numerical calculation. So I'm going to jump over to Python and we're going to do that. And let's see if we can get the value of pi. I don't know if this is going to work because I haven't done it before. So this is something new for me and you. We're all learning here. Okay, so here. Okay, so let's make this a slight bit bigger because people complain about that. Fake circle pi, that's what I'm going to call it. Okay, I'm going to need some constants here. K, let's say K is 1. I'm going to need the time of 0 and my time step. Let's start with the time step of 0.01. We're going to change that later. Okay, I'm looking over my notes here because I do need, let's just make a ball. Let's make the center. Center equals sphere. Position equals, put it at the origin. Radius, let's make it really small. Let's make it 0.01. That's fine. And then I'll make a ball is a sphere. Position is vector 1, 0, 0. So this starts off with a radius of 1, but it may not actually end up with a radius of 1 because I don't really know what it is. Let's give it a radius of 0.05, color yellow so we can see it. And let's have it have a trail. Make trail equals true. Save and run. I always like to run it after I start making stuff because you never know if it's going to like go crazy on you. Oh, see, that's not good. Let's make that a little bit smaller. There. You're just going to have to deal with that. Okay, so there's my center. There's my sphere. I think that looks good. Okay, so now I need to do some other things. Let's say ball.m equals 0.1. Ball.p, the momentum, ball.m times vector. I want to go in the y direction. Let's say 0, 4, 0. I'm just guessing here. I don't know what's going on. I don't know anything. Okay. I think I'm ready to start. Let's say while t is less than 4. Rate 100. So the rate 100 says don't do more than 100 calculations per second with a time step of, oh, you couldn't even see that image because I covered it up with my face. There. Okay. So with a rate of 100, that will do no more than 100 calculations per second. So the first thing I need to do is calculate the vector r. So r is going to be the vector from the center to the ball. So it's going to be ball.pos minus, oh, you got to spell it right, ball.pos minus cent.pos, and cent stands for center. Now I can calculate the force, F equals negative k times r. Now, this is really nice because r is already a vector. So I don't need to find a unit vector or anything like that. I just do it. Now I can use that to update the momentum. So ball.p equals ball.p plus f times dt. Now I can update the position. Ball.pos equals ball.pos plus the velocity, which is ball.p divided by m times dt. And dot. And then update time. And I think that should work. It's not going to give me I don't think it will give me a circle. There you go. Not a circle, but it is in 3D. Okay, so now we need to make it have a circle. So I'm going to add another parameter in here called b. And let's put b equals 0.1. I think. And that's the drag coefficient. That's what I'm calling the drag coefficient. So now my force, okay. How do I get the component of the momentum in the r direction? So imagine, let me switch back over here to the paper view. So imagine that I have my center, my ball, That's the vector r. That's the vector p. And I want this component of p. So this is the same as the unit vector r hat is in that direction. And if I say p dot r hat, that's equal to the magnitude of p times the magnitude of r hat, which is 1, times the cosine of the angle between them. That's that. So this is p dot r hat is the component of p in the r direction. So I can use that. And the dot product's built into Python. So let's just say, let's call this f drag. And that's going to be equal to negative b times the dot product of p. Actually, I want to do the velocity. So let's do ball.p divided by ball.m. That's that, comma, r hat. So norm r. That's r hat. Now but the dot product returns the component in the r hat direction. So I need to still multiply by r hat to get it back to a vector. I think that works. And then this is just going to be f plus f drag. Let's see what happens. I think I'm going to need to run this for a longer time. Let's run this for 8 seconds. Okay, you'll notice it did not get back to the same orbit, and it does indeed look like it's turning circular. I mean, it's hard to tell with the visual eye. We'll analyze this in just a second, and that's actually the first thing we do. How would we know it's moving in a circle? Well, we would know if the radius, the distance from the center to the ball, remains constant. So let's make a graph. T graph equals graph. X title equals time. That's just called t in seconds. And then y title is r. I'll just call it r in meters. It doesn't have to be 1, right? So f1 equals g curve. Color equals color equals color dot blue. And then down here, I want to plot that. I want to plot r versus t. So I'm going to say f1 dot plot. The x value on this is going to be t. The y value is going to be the magnitude of r. Yes. I think that's right. Okay. So you'll notice it is kind of narrowing in on a particular r value. I'm running too slow now. It's driving me crazy. So let's put this at 10,000 and let's run it for 20 seconds. Now the display is going to get messed up but that's fine. See, because it doesn't really display it correctly. But you'll notice here that it does indeed zoom in to a particular value. And that's my radius. And this happens after, let's say, 15 seconds. 17 seconds. After 20 seconds, I think it should be good. Let's just go ahead and print that. Print r equals mag r, just for fun. And it gives me 1.1234. Okay. I think that's a circle. Now, let's do this. I'm going to cheat. Print v. And this is going to be equal to mag of ball.p divided by m. So how fast is it going? What's the velocity? So now, if I go down here, I get 3.56. So I'm going to use these two values. And up here, I'm going to put the ball position at 1.12334. I'm going to put the ball's velocity at 3.5614. 1, 2, 6. Now I'm going to run it. And I'm going to turn this rate down to 100. That's fine. Well, whatever. And it's not in a perfect circle, right? But it's pretty darn close. And look at these values. They're oscillating. They're still changing. It's still getting into a better and better circle. Maybe I could even increase this drag by 2. Maybe it'll get there quicker. Let's see what that does. I mean, those look like a big oscillation, but it's not. It's going from 1.15 up to 1.55, so it is kind of big. Huh. Kind of disappointed. I thought if I gave it that initial velocity, did I not use the right ones? Let's see. Well, I'm gonna go with this anyway. Let's see if this works. Okay, it's working again. I'm really surprised that my values didn't work. Oh, see, now it has a velocity of 2.99. Huh. Well, let's try that. So velocity of 1 point. This is different. Let's try that. Let's run this for 40 seconds. That way we'll know. I changed that. I'm really just procrastinating here, aren't I? Okay, so it should be settled out. And I get, let's use these numbers right here. 1 point, and now I'm going to stick with these and be done with it. 1.33678, and then the velocity is, and I assume it's perpendicular, right? So it'd be 2.99283. Let's run it again and see what happens. That looks nice. Yeah, and you see here the oscillations in R are very small, and I could do this again, right? I could put in these new values, but I think we're done. We're done with that. I have that. Now the next thing I have my R. Next thing I need to do is calculate the circumference. So I do need to take the distance between each time step and add it up as it goes once around the thing. So let's do. Let's go back to the paper real quick. New sheet of paper. So here is my circle. And so here's the ball right here, and then here's the ball at the next time step. So this is, let's call this R1, and this is R2. So delta R is going to be this vector from here to there, and that's going to be R2 minus R1. So I'm going to need to record the previous position. So I'm gonna start here, and I'm gonna set this equal to R old, and then I'll calculate the new position. That way I can find, oh, actually I have delta R. Delta R is equal to, let's see. So if I say V average is delta R over delta T. So this is delta R. It's just going to be P over, I think I'm going to do it this way. I'm going to do it this way because I think it'll give me better answers. I'm not going to use this P over M times delta T, which is what I use to get delta R. I'm not going to do that. Instead, I'm going to do it this way. I'm going to write down the old one, and then once I calculate that, I'm going to take the difference between these two, and that will be this vector. Then I need to find the magnitude of that, and I'll just add it up. So I'll say C equals the sum of the magnitude of delta R. And so I'll go through the whole circle. Now what I need to do is say I'm going to start with x and y equal to 0 or close to it, and then I stop when I get back to that same location. That might be a little tricky. How do I do that to get one complete loop? I'm not 100% sure. Okay. Well, let's just start doing it. We'll figure it out as we go. Okay, sorry about that. So we have run this long enough such that it should be in a stable orbit now. So let's start doing things. Let's run it again. Let's just see if we can make it run for one more loop. So I'm going to print, let's say, it's at a particular location. I don't even know what that is. It's at an X and a Y location. I guess I could calculate the angle. Let's try that. Okay, so theta equals a tangent. I don't think this is going to work. Of ball.pos.y divided by ball.pos.x. Let's just print. Now, that's my angle, but I think it gives me double angles. So I don't really want to do that. Okay, let's just say this. Start equals ball.pos. That's the starting location of this circle. Now what I'm going to say is run. Run equals true. How about this? We're going to cheat. So while run, do the following. I'm not, I guess we should do the rate. Rate one, something big. Let's do it not too big. So do I stop? So now I also need to do this sum. Let's call it C. C equals 0. So I need to add up to that. And then I'm going to say R old equals ball.pos too, right? Because I need to start with that. Okay, so the first thing I'm going to do, I need to have all this stuff in here. I need to have do all this calculation still. Okay, so the first thing I'm going to do at the beginning of the loop is calculate R old. No, I need R old. I already have that. Okay, so R old will be down here. I always make a mistake here. So let's put R old equals R. Okay. Now, do I stop? Do I stop if, let's say, if the distance from R old to R start is super small, then I've made it all the way around. So let's say this. If magnitude R minus R, no, R old minus start is less than 0.01, then run equals false. Yeah. So I'm going to set run equal to false, and it'll stop running, right? No, and t is greater than. It's going to take at least a second to go around it. So let's say t is greater than 42, because I started up here with 40, and I know I'm doing this all messed up, but come on, just give me a thing here. So now I'm going to calculate the circumference. So C equals C plus mag of R old minus, no, I need to do that up here. No, let's see, where did I do that? Up here, before I do that. So I have R old already, so C equals mag of R minus R old plus C. Okay, let's just see if that works. So now I'm going to say print R equals R mag R in meters. I feel like this is not going to work. I feel like I've played with the demon inside the computer, and I'm going to lose. C equals C, the circumference, in meters. And then pi is going to, let's see, let's calculate pi, p pi, because pi is reserved. And it's going to be C divided by 2 times mag R. If this works, I'm just going to be so pumped. Print pi equals p pi. There is no units. Okay. I'm just hoping it doesn't get stuck in an infinite loop. But I'm open to that possibility because I wrote the code on the fly. Okay, so there, now it's going in its final circle. We can watch it. That's kind of artistic though too, right? Oh, it didn't stop. It didn't stop. Okay, how about this? How about I make my time step smaller? Oh, it did stop. Okay, we're still in the settling down phase. Now we're in the... Okay, that's too slow. Too slow. Okay, here we go. Oh. The distance... It went half a circle. Oh, maybe... No, distance... Our start... was down here. Let's see what it got for pi. What? It worked. Huh. I don't know why it worked, but it did. So I got 3.134. Let's make the time step even smaller. I'm going to count this as a win because I don't know what I did wrong. And let's do this. I don't know why it stopped. Let's try it again. So there it goes in its final loop. There, see, it didn't actually quite get to the beginning, but I think that's a solvable problem, right? And I got the same value. I think this is close enough that I'm happy in the idea. And you can play around with this for your homework and make it even better. But the most important thing is this code is a little complicated, but not too terribly complicated. But there's no pi in here, right? There's no trig functions. There's nothing like that in here, and we can still calculate pi. I'm pretty happy. Okay, I'll end there. I'll talk to you later.